Welcome to Superheroes of Science. I'm Steven.
And I'm Sarah. We co-host Science from the Experts. Our guests are professionals doing cutting-edge science right now.
They're experts in their field discussing what they know best. So listen up and learn real science from real people.
Subscribe now and stay informed of our latest episodes and show your support.
Joining us today in Superheroes of Science, we have Disha Okhai, PhD candidate here at the Department of Earth, Atmospheric and Planetary Sciences at Purdue University. So welcome, and thank you for joining us today.
Yeah, thank you for having me. I'm really excited to talk to you guys about my research.
Well, that's exactly what we want to hear about.
Yeah.
Well, let's start. What are you researching?
So I am on the geology side of things, and I study volcanoes. Thankfully, ancient volcanoes, so nothing that's erupting right now. The current place that I'm studying is 28 million years old. And what happens is, as you're forming your volcano, right, you have this like textbook example of this giant magma chamber, right, like this big tank that's colored red, usually in your textbooks, right? So we are trying to figure out how those form. And usually they don't form as this giant tank, right? They form in small increments. So you have like little bits of magma coming in. Sometimes they just freeze on their own just because they're really little and the surrounding rock is really cold. Other times they actually kind of coalesce and form this bigger system. And when they form the bigger system, there's a lot of processes that can happen. So imagine cooling this liquid, this really, really hot liquid. So you're at anywhere between 1200 to 800 degrees Celsius, right? You're like cooling and you're forming all these little mineral crystals. Usually the minerals are really dense, so they sink, right, relative to the liquid. And so you start to create these differences in the chemistry, right? So there's minerals that want to go into, there's elements that want to go into these minerals as they're forming, and then there's other elements that don't like to be in minerals, so they want to stay in the melt. So you start to generate these patterns in terms of the chemistry, where you have certain elements that get concentrated in the melt, and then others that kind of form and concentrate in these minerals that are sinking. Mm-hmm. And so understanding these kinds of processes can help us figure out the hazards of these, right? So one of the elements that gets concentrated in the melt can be silica or silicate, and that is what generates these really large explosive eruptions. So we want to know if we have this situation where we're really focusing and concentrating this and then thinking about the sorts of timescales on which those processes are happening, right? So it's like, if it's happening really quickly, are we having like tens to hundreds to thousands of years to, figure out what's happening in the system? Or is it just like you kind of make your magma, everything really starts to crystallize and cool really quickly, and you can generate this really high silica thing that can erupt at any moment?
All right.
So
I want to stop for a second.
Yeah.
And I want to back up just a little bit.
Yeah.
And let's start with a little bit lower level before you start telling me the chemistry makeup of each of the elements within the thing. There's different types of volcanoes, right?
Yes.
And so what are they?
So a lot of times
dome or shield volcanoes.
Yeah, so you have shield volcanoes, you have stratovolcanoes, and all of these, the shapes are kind of determined by the kinds of lavas that come out of them.
Okay.
Right?
And so when you have a magma chamber, is that only in one type or is it in both?
So all of them have magma chambers, which is where you're getting your liquid that erupts out, or your ash and other, fine particles that erupt out. And it's the composition of that determines what kind of a landform you form, right? So, for instance, shield volcanoes they have these really wide sloping sides, and they're usually made out of basalt, which is really flowy. So imagine if you took water and you poured it upside down on a table, right? It's just going to flow out.
Okay.
If you took honey, on the other hand, and flipped it upside down on the table, you'd have a while until it actually gets to the table, and then afterwards it doesn't just like flow like the water, it takes a while to actually spread out. And so things like rhyolite and then andesite and dacite, which are all different compositions of magma, will have different viscosities, which means how far they can flow or how much they can flow. And so those really play a key role in forming that landform, right? Where it's like, if it's a really thick, viscous magma, then it just can't flow. And so it either ends up creating these really steep landforms, or it ends up exploding because it just has a hard time, coming out.
All right, so with this type, then you're studying the past chambers, so what's below those volcanoes.
Yes.
Is what you're studying. How are you studying? Because I'm envisioning under the ground this huge mass of rock.
Right.
And how are you studying that?
So usually how we study, magma chambers, when they freeze, just turn into rock, right? We're thinking things like granite that are on your kitchen countertop, or...
And that's the second time you said freeze. When I think of the word freeze, I'm thinking of it's below zero, it's frozen. But you're using the word freeze slightly differently.
Yes.
It's just like turn into a solid or solidify?
Yes. So solidify and then freeze is also... So solidification can happen at a range of... solidification can look very different, right?
Uh-huh.
So you could have something that's crystallizing really slowly and cooling, and eventually it solidifies, right? Where it's just like all a rock now. If you're cooling very slowly, you could form like nice big crystals. If you cool really quickly, right? So if you have a really small amount of magma coming into really cold surrounding rock, you just put it in and instantly it freezes, right? Kind of like if we have a snowstorm outside and you're throwing a glass of boiling water, right? Like it instantly freezes where you just don't see. So if something like that happened with magma, you just see like a frozen bit of melt or glass because there just wasn't any time for it to really grow any crystals within it. Yeah, so I think I use frozen and solidified kind of interchangeably.
Okay.
Yeah.
Okay.
Yeah, but when I say frozen, I just mean it's solidified and now it's rock.
Well, I want to make sure.
Yeah.
I mean, if it's buried, can it be frozen if it's buried? So I'm like running all these questions in my head. I'm like, all right, I got to find out.
So it's gone from the molten, like the lava, really hot top,
Yes.
to now it's cooled enough that it's this solid rock, but it might be different.
But so the compositions determine, and the time scale at which it's cooling, right? So if it cools really fast, you might just see like something more like glass, right?
Oh, wow.
Or something that has really fine grains, or really fine mineral grains that you can't really see with your eye.
Right.
Whereas if it's just like sat around for a long time, you actually start to form these really nice minerals that you can see.
Okay.
Just like if you grab that rock in your hand, you'd be like able to say like, oh hey, there's some quartz, there's some feldspar,
All right, now you go back. I mean, finish answering the question that you started answering on how you research that. How did you figure that out?
So the place that I'm currently studying is in Nevada, and what we have there is this fault has essentially turned a whole system sideways, which is really cool. And so we have this entire like tilted section. So literally imagine you have a bunch of volcanic stuff, you have your frozen magma chamber, your solidified magma chamber, and the entire thing just got turned to its side. So
it's just
now,
over the millions of years with the plate tectonics.
yeah, so this is associated with like the Basin and Range extension in the southwest US, where essentially as the tectonic plates are moving, you're getting these areas of extension and compaction just to accommodate that movement of plates. And so you just get this fault and you essentially just like turn this entire like section sideways.
Yeah.
So we have this area where across 10 kilometers, you have about 5 kilometers of this frozen pluton, which is what we call like frozen magma chambers or solidified magma chambers. So you have about 5 kilometers of this pluton and then about 5 kilometers of the volcanic rock, and it's all intact.
Oh.
So they're all like, you have volcanic rocks on top of this plutonic area. And so I'm essentially trying to figure out what happened with the pluton and how this magma chamber was forming, and then thinking about the volcanic part to be like, well, did we have things that were erupting as we were building this magma chamber? Or were the eruptions coming from somewhere else or something else? Just thinking about how frequent the eruptions were. What are the compositions, right? Are they big explosive eruptions or are they small, just like you kind of burp out a little bit of lava and it just flows off and nothing happens? So.
And it's just the type of rock is.
Yeah, so the type of rock and then the type of formations, essentially. So if you have a lava flow, you see that there's a lot less bubbles. It's more, it's all more cohesive. You have a lot of crystals in it, and then there's a unit that you call a tuff, and it's essentially just like it's almost chalky, where it's just made up of ash that all compacted. So if you had an explosive eruption, you get these, pieces of ash and other pieces of rock and everything that's essentially getting blown out of this volcano, and then everything essentially compacts, and you have some hydrothermal system or some water running through it, or just with the heat, it kind of fuses together. And so you see these different textures within the rocks in the field, and you can figure out what sorts of eruptions they are related to.
Okay.
Wow. So you had said some of the silicates that might be linked to more explosive.
Yeah, so all the so when you concentrate silica, which is SiO2, in your melt, those are really, really viscous.
Okay.
And so those tend to be the explosive ones. So what ends up happening is, because it's so viscous, you might end up plugging the volcano as it's trying to erupt, right? Or it's just not easy to flow it out, right? So think honey, think tar, right? You're just imagining trying to, get tar out of a volcano, and you just can't, and it gets stuck somewhere, and then you just have to explode or do something to, release that pressure or get that little slug out.
Interesting. Now, are those things you would see in a really ancient volcano, or does age matter? Does age matter?
No. So we obviously study ancient volcanoes for a couple of reasons. I mean, one, safety. It's nice to not have to be near a volcano that's about to explode. The other part of it is, a lot of times when you have active volcanoes, you don't necessarily have exposures, right, of anything, unless your volcano brings out, a chunk of the magma chamber, or a chunk of something that underlies it. So a lot of these older systems actually have been, due to folding and other plate motions, have been exposed and are easy to access, right? Because it's you can't really drill down. You also don't want to drill down if it's an active volcano, or you're not
Good point there.
Makes a lot of sense.
Yeah. So it's the ancient systems are just studied as a way to try to figure out what sorts of processes are happening within these systems, and then try to see if we can apply it to modern systems and learn something.
And how would it be applied? So you're doing the research on the ancient, you're figuring out the components of it. So if it's a shield, it has this, and we're finding this is happening in it. Then if it's the other type, shield.
Explosive or
Stratus.
Yeah.
Stratus. Oh, man. Thought I'd never taught this. But it has different things going on. So you're figuring out what happened. Then how does someone then take that and apply that to what's happening today to help us have a greater understanding of what's happening in the world today?
Yeah. So I guess there's two parts of it, right? First, it's as you start to understand this magma system that's feeding your volcano, we can start to think about monitoring a little bit better, right? So current monitoring things include, people put a lot of GPS stations, right, to figure out is there some sort of tilting or bulging happening on the volcano, right? So it's if you're assuming that some magma body is growing underneath, you might see, the volcano kind of start to grow, and you might see it start to balloon outwards. So just thinking about, if things are going really fast, that might not be a good way to figure out whether anything's happening, right? If you're just very quickly collecting your magma and it's just turning into something that's eruptible almost immediately, you're not going to know, right?
Yeah.
You're going to be oh no, our GPS stations are showing something, and then suddenly it explodes. I mean, usually it's not that fast, but it's just thinking about how effective a lot of the systems that we currently have in place are, right?
Yeah.
So a lot of the systems are monitoring the sorts of gases that are coming off. So things like sulfur oxides, nitrous oxides, carbon dioxide, right? To be if you think that you're starting to kind of bubble up and release some of the gases, is that an effective way to figure out what's happening in the subsurface? So just kind of evaluating how well those systems can truly, measure or predict the hazard. And in terms of thinking about timescales for evacuation, there's literally millions of people around the world who live at the foot of multiple volcanoes, right? It's very fertile land. basalt makes a really good, planting area, but then there's also lots and lots of hazards associated with living in places like that. So I think hazard monitoring is pretty important. The other part of it is trying to understand the relationship between the volcanic parts and the pluton or the magma chamber beneath. It's helpful to think about, well, if you're growing a magma chamber and you're not erupting anything, what does that tell you, right? Like, are you seeing all these eruptions and then you just have this time where you're growing your magma chamber and then you have some amount of time before the next eruption? And does that help us kind of predict things better? And a lot of times all these systems are slightly different, right? Like, they're different compositionally, they're different based on location, right? Where is this magma coming from? Is it a hot spot? Is it, subduction related? Because there's so many different geologic places where you could be generating magma. But I think the other part of it is just starting to get a general sense for what these systems are doing, how rapidly they're evolving, and then also thinking about how the volcanics and the subsurface magma chambers are interacting with each other, I think have a lot of applications.
Now, a magma chamber, what's below it? Is it solid rock? Or is it just like, does it go deep enough? It's not solid rock. I mean, is it the lost land before time? Dinosaurs running around? What's down there below a magma chamber?
So it depends, because you can have magma chambers at different depths, right? You could have something really shallow, so in like the upper 10 kilometers of the crust, your crust is generally about 30 to 40 kilometers thick, right? So you could have things that are deeper, that are very close, that are getting very close to the mantle, right? So everything could be kind of warm and, I guess, mushy, for lack of a better word, where it's just all hot rock, so it's not necessarily solid, but it's not necessarily liquid. So I think it really depends on where you are in the crust, right? Because you have one control on what that looks like is how hot is everything around it, right? You have the geotherm where it's you're roughly heating 20 degrees Celsius per kilometer that you go down, right?
Wow.
So it's if you're thinking you're at 10 kilometers, that's 200 degrees Celsius. Okay, that's hot for us, but for, most rocks are still kind of solid at that temperature. Then you go down another 20 kilometers, right? And you're really getting hotter and hotter, and you're getting to this stage where you kind of have these semi-molten rock situations. So it's not, unfortunately, I don't have a very good answer for your question. It really depends on.
I don't expect you to know everything in all the related fields of what I'm asking, but I might be out of bounds even further with this question. But how does molten rock get into the upper crust? A magma chamber that's below the earth, the upper crust.
Yeah.
How does it get there?
Okay, so these are some of the questions that we're still really thinking about, right? Mm-hmm. So there's 3 main controls on building magma chambers, right? You need space, where are you going to put that? Where are you going to put all that liquid? You need a source where the liquid is coming from, and then you need to be able to transport it, right? Because your source is somewhere deeper in the crust. So typically, because deeper in the crust is really hot, just like we were talking about, the source is probably not really a limitation. It's probably easy to just generate a lot of molten rock when it's really hot. In terms of transport, usually diking, which is essentially you generate some pressure and then you just essentially push apart the rocks and you create this pipe-like channel, right, that propagates upwards. So you just have a dip that ends up widening until you hit some sort of a layer where there's either some sort of a difference between layers, or there's some sort of a pre-existing weakness, right? So if you already have cracks in your rock or something going on there, then you end up kind of pulling your magma out through the crack or the dike. And that process can be really quick, where you can, if you have, there was a really cool paper from I think it was the 70s or the 80s, but they basically did this calculation where they were if you have a dike that's tens of meters wide, you can essentially fill up this giant magma chamber in a couple of years. It's just super fast. This process is just really, really fast, and you don't need a big Like, as long as you have something at the bottom that kind of keeps this, keeps it open because there's stuff flowing through it, it can be really, really fast. Yeah.
I have one more question. If you have a magma chamber, does that mean you definitely have a volcano? Or can there be magma chambers and no volcano?
So, I was like, this is the interesting, and that's one of the things that we were trying to find out. And in this system, it looks very much like we see a couple of eruptions. Mm-hmm. We see the system suddenly transition to building this like magma chamber or this pluton. And there's nothing. There's nothing coming out on the volcanic side until like 3 million years later.
Oh, wow.
3 million years later?
Yeah, 3 million years later. So it's just, I mean, this is literally like something that it's an excellent question. It's something that I'm thinking about, right? Because it's like, how do these things work, right?
Yeah.
And in this system, it really seems like there's just nothing.
Wow.
Yeah. Yeah.
All right, I know you said that was the last question, but I want to make I want to stop some of the trolls real fast. Because whenever we put something out, my internet trolls drive me nuts sometimes. And you had said when we make a volcano, when we make a chamber, I just want to make sure that people know that humans don't make them. It's just a natural process.
Yes.
You're referring to that.
Yes.
I just want that clarification to stop, because every time we put a video out, I have someone, she said, we make a volcano.
Oh, brother.
They're making those volcanoes. I knew the government did it.
Oh, no.
So I thought,
the government.
just,
Oh, no. Now I'm worried.
I just thought, I wanted to make sure that
Great.
That's a good clarification.
we clarified that people don't really make them. It's how they're made in nature.
Yeah, I don't know how, should I just, re-say that part, or I don't know.
Oh,
no.
Just
Once you can confirm it doesn't.
Yes, it just gets
Okay, good.
It's a natural process.
Scientific confirmation. Oh, no.
I gotta think about these things. I approve all the comments and reject them and wonder, what are you thinking when they ask these questions? So I just want to make sure we get that out there. It's people don't make volcanoes.
Well, I think when you're just talking about some of these things that are so abstract, you just have to have normal conversation about it. And so you don't think, I think that didn't even think about.
But people aren't
You're
normal.
right. Absolutely.
I know they're not. I read their replies. They're not normal. We got to think about these.
Yeah.
Even superheroes are not immune to trolls.
Good point.
Thank you for your time.
Yeah, thank you for having me. It was really wonderful.
Thank you for listening to this episode of Science from the Experts from Purdue University Superheroes of Science.
If you like this episode, subscribe, give us a positive review, and share the love. Boiler up!
Hammer down.